Hi, this is Linear Algebra 5.2 characteristic equation. This is the characteristic equation that we're going to be using, and that's what they call this. And so we're going to be using that to go ahead and find eigenvalues. We're going to be doing 2 by 2, 3 by 3, and triangular matrices. And we're going to use the characteristic equation, this thing right here, in order to do that. Row reduction, I decided not to do. So if we want to, we can look at maybe some LU factorization and see what happens with the eigenvalues for that. Okay, so we're going to go through the process now of finding the eigenvalues of this matrix right here. So first of all, we do know that the determinant, this right here, is equal to 0. And so what I want to do is go ahead and take matrix A and subtract out lambda I. And so I'm going to set this up. A minus lambda I. And what we want to do is go ahead and find the determinant of that. So I'm going to go A times D minus B, C times B. Okay? And then that would give me my determinant. So here's my setup right here. And so I did exactly what I said. I took the determinant and I'm going to set it equal to 0. So when this is 0, that would give me my eigenvalues. And moving on, go ahead and solve this. Pause this if you need to, and you can solve this for yourself. If I simply get a quadratic, organize everything in descending order, now I can go ahead and factor. Factor, and I get the two values for my eigenvalues. There are my eigenvalues right there, 8 and 2. I had them over here, so that was my target. Now I want to go ahead and find a basis for the eigenspace, and this is what we did in 5.1. And just to refresh, a basis for the eigenspace for A for each lambda. So what I'm going to do is take 8 and plug it into this matrix right here. So I took the 8 and put it in here for lambda. And so 5 minus lambda would give me my negative 3. The 3's stay, and then I get another negative 3 over here. So a lot of symmetry going on here. This is an augmented matrix, so you might want to put a line right here, and then so that's my values equal to 0. Okay, so now all I do is a row reduction on this in order to figure out what my vector is for the basis for the eigenspace. This one turned out quite nice. This row just wiped out by adding the 2. And notice that this was dependent, and so that's what has to happen in order for this to give me my situation, so I have the eigenvectors for that. And so then I have this 1, negative 1, and 0. So I can set that into an equation where x1 is equal to x2. And so that's what I end up with. And then so 1, 1 is going to be the form of my basis for the eigenspace. Now it could be 3, 3, it could be 15, 15. All those would work because they are all just multiples of this 1, 1. Multiple of 1, 1 would be an eigenvector for us that forms a basis for this situation. And remember in our last unit, we showed that this was a vector, and so the space would be anything that was on the line that included this vector. That's the eigenspace. Okay? Why don't you try lambda equal to 2, pause this, and go try it for yourself and see what you come out with. So for lambda equal to 2, it sets up very similar, and we get this situation right here. Okay? Now, how do we know that we did this correctly? Well, if I take my original matrix A and multiply it by any eigenvector that I do have, then I should get a multiple of this back. And so let's try that and see. In fact, in this case, it should be a multiple times 8. And over in this case, it should be a multiple times 2. Enough on my old Desmos calculator, I took A times C. This was my original matrix. This is the basis that I said. So A times C is equal to 8 and 8. So that would just be a multiple times 8. 1 times 8 gives me that. Similarly over here, well, that copied wrong. Hang on, the correct one. So A is here, and then C is 1, negative 1, which I got over here with lambda equal to 2. And if I multiply 8 times C, I get multiplied by a factor of 2. That's my lambda. Okay, so the matrix is doing the same thing as what a constant does. In the gift, you have to do the same thing with a 3 by 3, but it gets kind of clumsy to solve if you're going to go ahead and solve it. I think some of the problems just give you setup, but if you wanted to go ahead and solve it, make sure you use technology. And then make sure you can do 2 by 2 by hand and 3 by 3 with the technology, as I mentioned. Okay, so now we have our last example. Find the characteristic polynomial of the following matrix. So I have the matrix here. Notice it is a triangular matrix. And with the triangular matrix, what do we know about the determinant? Well, we're just going to have to go down the diagonal. And when we do it with the lambda involved, this right here, this matrix, then we know that the diagonal values are just going to give us whatever our eigenvalues for this matrix. It does say characteristic polynomial. And so if I take this lambda minus 2, lambda minus 4, lambda minus 2, and lambda plus 1, and I put that, and like I said, I know the determinant is just going to be along the diagonal with the triangular matrix. All I have to do is set up the polynomial as such. Notice I put a squared here. That's multiplicity 2 for this one value, if we had to find the 0 of it, but then we do call that lambda. So if they do ask us then for what are the eigenvalues of the triangular matrix, oh, I forgot. This polynomial, if they want polynomial, they usually want to expand it. So we'll do expansion first, and then write out what the eigenvalues for the triangular matrix and what they. So here's the expansion. So this is the polynomial that you need. If you wanted to do that by hand, go ahead. Otherwise, I use technology for that. And then for part B, what are the eigenvalues? The eigenvalues then would be 2, 2, 4, negative 1. Should I list this twice? And the answer is kind of yes, you should. Or you could say that lambda is equal to 2 with a multiplicity of 2, like we did with zeros back in your algebra day. And then we also have 4 and negative 1. So either one of these ways would work. All right, that's all I'm going to do. There are some applications in this unit. And so you can look at some of that for maybe one of your projects, and it does link with Markov chains. And so check that out. And then your gift is here. Notice 28 or 29, you pick one of those to do. All right, I hope you enjoyed this and get after it. Go ahead and find some eigenvalues. Have a great day.